What if you could take a step back and look at the world? Explore the line between certainty and doubt. You are listening to the Illumination Hour with your host, Ellen Stallone. Hello, welcome one, welcome all, welcome to the Illumination Hour. This is me, your host, Ellen, and today we are going to be diving into the unknown, as I say in the intro. Exploring what is known versus what is not known. How many of you out there believe in aliens? Alright, that's a tricky question, right? Maybe aliens exist, maybe they don't. Who really knows? Have you ever gone to YouTube and tried to find evidence of aliens? That's probably the worst place to go because there's confirmation bias all over that. Like, if you go and look for alien videos, you will surely find those. But they probably are fake. Most of them that I've seen recently don't look super realistic. The camera's always shaky. It looks like a doll that somebody sprayed with oil, so it had more of a realistic skin tone. Maybe it just looks like plaster or an obvious setup. And why do the cameras shake so much? I mean, nobody's hands are really that shaky. Or they just not paying that much attention because they're saying, "Holy shit, I found an alien!" I would be super creeped out if I did find one. And bravo to those YouTubers that do film those alien interactions, but at the same time, come on, is it real? Just tell us. Give us the answer. We want to know. Because there's so many people saying that aliens are here, they exist, they're coming. And yet, what is the actual evidence? Where's the scientific proof? Well, our culture today has created an entire genre dedicated to these alien lovers. It's almost the 4th of July, and the movie Independence Day just came out the other day. I went to see that with some friends, and surprisingly, it was an amazing film. There were some really creative concepts in there, like gravitational fields, and the drone society, the hive mind society of the aliens, as opposed to the individualists that we are. There was a lot of fascinating concepts there, but at the same time, you know, this alien hype, while there's many theories going around this, perhaps they're priming us for the time when aliens actually do show up. Perhaps they're trying to convince all of us humans that we need to band together under a new world order, have one government, so that we are all working together more closely. Or perhaps this is just a film that says, well, look at us humans, we're pretty great, we can take over any alien species, no matter how advanced it is. Which I thought the film was more realistic at the beginning when it took out all of Earth's defenses, even the stuff orbiting the planet, just like in one shot. We were helplessly outgunned. I think that's how it would really be. A spaceship the size of the Atlantic Ocean. Come on, we're dead. There's no way we're surviving that. Well, in the movie we did, but I also wanted to talk about that. This movie, is it really healthy for some people because it's just hyping up this fantasy of aliens being here attacking us? You see, many conspiracy theorists have these stories and fantastical ideas about what aliens are doing here on Earth, but in reality, we don't have any scientific documented evidence. Nobody sees them. Perhaps there is scientific documented evidence somewhere in the world, but we as average people, are not privy to that knowledge. We aren't allowed to touch it or see it or know about it. And even if we were, it may be censored to the point of unrecognition. So, as people who work outside of Area 51, because we all know that that's where the aliens are kept, we have to rely on our scientific minds. So I'm not denying that aliens do exist. In fact, I have a story here that I want to read to you about aliens discovered above us. Now, where else would aliens be discovered? Well, this story is actually kind of a shocker. It comes at you from the side. It's not what you would expect. Scientists have recently discovered what may be alien strands of bacterium in the upper atmosphere. Oh, I got you. You thought it was going to be real, like, intelligent aliens. No, this is just bacteria that are unlike anything we've ever seen. And they were found in the upper atmosphere of our planet, which is pretty high up there. Most things die before they even get to that level. The bacteria found have absolutely no resemblance to anything on this planet, making the discovery one of great importance. While it's not yet certain exactly where the bacterium is from originally, there are still things we have yet to discover in this incredibly enormous universe. There are 4 strains of bacteria, and they've been found at the edge of space. Brand new discoveries. Scientists think that they might be there of their own doing, which means they weren't brought up there by a balloon, and they might not be from Earth at all. Some scientists have argued that carbon and water-based life from other planets might look a lot like life from Earth. So we can't rule out the possibility that these bacteria strains are, in fact, from another world. The very possibility that these bacterium strands are from somewhere other than Earth is fantastic. Alright, so bacteria are found high above our atmosphere. And the story says that they don't resemble anything on this planet, yet they do. That takes a lot of complex explanation. I mean, perhaps they're carbon-based, which makes them similar, because here on Earth, much of life is composed of carbon-based molecules anyway. Perhaps they need water, just like we do. Where, on Earth, everywhere you find water, you also find life. Perhaps that's what they mean when they say that they look very similar. Okay, well, let's go on to another article that covers this a little bit better than the last one. Alien microbes found floating in the stratosphere. Ooh, it even tells us where in the atmosphere. Oh, and it was the Brits that found this alien life. British researchers. They found alien life arriving on Earth from space. Our hopes of finding life on Mars were trashed after NASA's Curiosity rover found no traces of methane on the red planet. Oh, by the way, this article was written in September 20th, 2013, which is a long time before they discovered that there is, in fact, water on Mars. So, just take that with a grain of salt. Anyway, a new study from the University of Sheffield assures us that there might be life beyond Earth. The team, led by Professor Milton Wainwright, has found microbes which they believe could have come only from space. The alien microbes were found on a specially designed balloon that was sent 27 kilometers, or for you Americans, it's 16 miles, into the stratosphere during the recent Perseid meteor shower. Most people will assume that these biological particles must have just drifted up from the stratosphere from Earth. But it's generally accepted that a particle of the size found cannot be lifted from Earth to heights of, for example, 27 kilometers. The only known explanation is by a violent volcanic eruption. And none of those have happened within 3 years of the sampling trip. And since there are no other events explaining the presence of microbes in our space, Researchers believe that these microbes could be the proof that life exists elsewhere. Our conclusion is that life is continually arriving to Earth from space. Life is not restricted to this planet, and it almost certainly did not originate here, Wainwright added. The balloon used in the study was designed by Chris Rose and Alex Baker from the University of Sheffield's Leonardo Center for Tribology. It had microscope studs that were only exposed when the balloon ascended to a height of 22 to 27 kilometers. The balloon was launched near Chester and landed safely near Wakefield. Analysis of the trapped particles on the studs shows that they had found a diatom fragment and some other biological forms that are too large to have come from Earth. Researchers said that they had taken precautions against contamination and maintained that both sampling and processing occurred in a sterile environment. The team is confident that the organisms have come from outer space. Wainwright and colleagues are understandably excited about this discovery. If life does continue to arrive from space, then we have to completely change our view of biology and evolution. New textbooks will have to be written. Previous research supports the idea that life or compounds necessary for building life may have hitched a ride on comets or meteorites. The team will be sending another balloon in October during Halley's Comet-associated meteorite shower. They are also aware about the controversy that this study will generate, and they welcome interest in the research. The absolutely crucial experiment will come when we do what is called isotope fractionation. We will take some of the samples which we have isolated from the stratosphere and introduce them into a complex machine. A button will be pressed. If the ratio of certain isotopes gives one number, then our organisms are from Earth. And if it gives another, then they're from space. The tension will obviously be almost impossible to live with, Wainwright added. Thank you, Wainwright, for your insights and your commentary. So, you send some balloons up into the atmosphere, you collect a bunch of microbes that you found up there, and you test them to see whether they're from Earth or from space. Well, which do you believe more? See, it's not all that surprising that little microbes show up from outer space, because microbes are little more than amino acids and a few other molecules just kind of clumped together in one glob. And that glob it responds chemically to its environment in a way that ensures its survival. Now, for as surprising as that may be, of course bacteria don't think. They're not the alien invaders that we all expected, the hyper-intelligent ones that are coming to kill us and take us out of our beds or crawl into our skin or probe us. No, in fact, these aliens are little more than space bugs. Where do they originate from, though? That's a good question. Where do they come from? They must have originated at some place where life was abundant at one point. Perhaps they adapted over thousands and millions of years to the harsh space environments. Who knows? We have insects and bacteria on this Earth that can survive space. So imagine if our entire planet was broken up and gouged out by other giant meteorites smashing into this planet. Some living things would survive, such as the tardigrade. Or I like to think of it as the water bear because it's so cute. But really, these things are beasts. They're space tanks. They can survive anything. And I'm sure there are other planets in the universe somewhere that at one point hosted bacteria or something similar to it, and then the planet was destroyed. And then those bacteria or small living things were sent off into the cosmos, where they drifted, waiting to be found by us. And we find them and just label them as alien microbes, even though everyone's definition of alien is different. Like most people, when they think of aliens, don't think of bacteria. But alien is a great catchphrase, don't you think? I mean, if I were trying to get website clicks, I would just put alien somewhere on the page, because there's bound to be tons of people looking for that stuff. So for as much as I would love to believe that in this vast universe of ours, billions and billions of light years away, somewhere in this massive bubble of existence, there has to be at least one other species that is intelligent, that is there to talk with us and let us know that we are not alone. We have cosmic partners that will help us expand or survive. And I know I'm not the only one, because there are massive installations of radio telescopes pointed at the sky. And this is an installation called SETI. You can look it up. Perhaps I'll talk about it soon. But the whole purpose of that is to communicate with whatever living things might be out there. But the probability of something like that existing is incredibly small. So I am going to try and quell some of your fears about alien invaders this episode, because finding an alien is about as likely as finding an elephant in the upper stratosphere. Not that it couldn't happen, but I mean, it's not going to get up there on its own, and we're not going to put it up there. So that elephant looking for a flight to space is out of luck. Okay, so let's approach this problem from a completely reasonable perspective. What is the likelihood that aliens exist? Well, one way that we can simply explain it without even having to do any sort of experimentation is through this mental exercise, this question that we can't seem to answer. It's called the Fermi paradox. This paradox is named after Enrico Fermi, and it's the apparent contradiction between the lack of evidence and high probability estimates for the existence of extraterrestrial civilizations. The basic point of the argument made by the physicist Enrico Fermi is that there are billions of stars in the galaxy that are similar to the Sun, many of which are billions of years older than Earth. So that in itself should make it likely that there's some other Earth-type planet out there, some planet that is capable of sustaining life and holding water and creating an atmosphere, and they're close enough to their star or their sun that they can stay warm at a nice temperature, but also not too warm and not too cold. So with all of these planets close enough to their star, being older than Earth, why are there not living things out there that we're detecting? Also, with high probability, some of these stars will have Earth-like planets, and if the Earth is typical, some might develop intelligent life. Well, the thing is, we don't know that Earth is typical because we've never really encountered another Earth-like planet. I mean, sure, we've detected them from thousands of light years away, but that doesn't mean that we've been to them and studied them. And how do we know that Earth is typical? I mean, there's probably thousands of times more planets out there that are not like Earth than are. It is also true that some stars will have Earth-like planets, because an Earth-like planet is just something that orbits the star at a nice distance. It's not too warm, not too cold, just in the Goldilocks zone. That is an Earth-like planet. It's perfect. And also, the end of the statement says, some might develop intelligent life. We also don't know how unlikely it is that intelligent life will form, because we don't know how unlikely it is that life will form, period. We haven't studied life forming on any other planets. We haven't even figured out how life formed on this planet. Now, once we get past that essential step from tiny molecules just floating around to them being something that works in cohesion with the other molecules around it, after we make that jump, then we can follow the evolutionary chain and figure out how unlikely it was that we developed as intelligent, sentient beings. Because we know that if we look back at the evolutionary tree, there were other species of proto-humans that were also intelligent in some way. They were better than the other animals around them. They learned how to use tools, and they still died out. Now, why was that? Maybe they weren't intelligent enough. But then again, how did we make it? We at one point were not intelligent enough. There are still mysteries that we cannot figure out, and probably will not, because none of us will live long enough to ever study something like that. Next criteria says some of these civilizations might develop interstellar travel, a step that Earth is investigating now. Yeah, well, investigating isn't good enough, buddy. We need to be actually doing it and testing it. Okay, let's assume that intelligent life did develop. Are they going to start traveling through space? Are they going to leave their planet? Okay, well, let's assume that they do leave their planet. They're looking for more resources. They need more metal to build more machines, to make more money. They need to keep more people alive. Okay, so they leave their planet and they go to the other planets that are in their little branch of the solar system. Great, okay. Now what? Now they expand to other solar systems that are in their galaxy. Now that's going to take a lot longer because galaxies are massive. They're made of millions of stars and planets. If they do eventually conquer all of the other planets that are in their galaxy, perhaps then they would have a reason to leave and to go explore other galaxies throughout the universe. What is the likelihood of that? Also, what if they are sending out signals or traveling around space and they just don't want to be found? Perhaps we need to be a little more considerate of these aliens' privacy. Anyway, even at the slow pace of currently envisioned interstellar travel, which by the way, it's incredibly slow. We haven't even sent humans to Mars yet, and that's like the next closest planet to us. How do we expect to send people through interstellar space? We haven't even had humans on the moon in decades. And you want to send people out through interstellar space? I doubt it. In fact, I doubt that within my lifetime we're going to be sending a human to some place like Saturn or Io. And I would love to see that. I think that would be really fascinating. In fact, I might even want to be that person on the shuttle. But the technical complications of that are so overwhelming that I just don't see it happening with the current technology that we have. We'll have to do a lot better to achieve interstellar travel. And I guess I'm kind of typical in that I expect that it's developing at kind of a slow turtle pace. But even at this slow pace of interstellar travel that's currently envisioned, the Milky Way galaxy could be completely traversed in about 1 million years. Whoa. So in 1 million years, maybe we'll have seen the whole Milky Way galaxy. That's too long. None of us are going to live that long. And that's too much information for one person to know, don't you think? Unless we somehow turned ourselves into robots, we're not going to live to see all of the Milky Way galaxy. Alright, but the point here is that if we were an intelligent civilization 1 million years ago, today we would have already traversed the entire Milky Way galaxy. I mean, right now, our solar system is kind of in the boondocks of the Milky Way galaxy. Like, we're in a little sidearm of a little sidearm. So we're nowhere near the center. We're just off to the side somewhere, pretty far away from all the action. So once we leave this place and start exploring, and we're super intelligent and we've seen everything in our galaxy, then we want to go to other galaxies. Now, perhaps somewhere in the universe, there is an intelligent species that has traversed its own entire galaxy. and they're ready to go looking for more. If that's the case, I'm sure that we would want to speak with them. And I mean, there's bound to be some existing, right? There's plenty of planets that have been around for millions of years that are capable of sustaining life. And developing intelligent life at that. And that intelligent life learning how to travel through space. Well, according to this line of thinking, the Earth should have already been visited by extraterrestrial aliens. I mean, the odds just add up to be that. In an informal conversation, Fermi noted no convincing evidence to this, leading him to ask, "Where is everybody?" There have been many attempts to explain the Fermi paradox, primarily suggesting either that intelligent extraterrestrial life is extremely rare, or proposing reasons that such civilizations have not contacted or visited Earth. Now, there's all sorts of reasons why aliens would not want to come visit us. I mean, we're not really the most pleasant species, after all. Look what we do to our own people. Kill, murder, steal, rule, control. It's not something that really advanced people want to see. At least I don't think. Perhaps it's very rare or non-existent. Well, just how rare and how non-existent is it? That's a good question, actually, and that is one that the Drake equation tries to answer. Now, the Drake equation is a probabilistic argument used to arrive at an estimate of the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. So just in our galaxy alone. I would like it to be about the entire universe, but we don't even know our own solar system. So the whole galaxy that we exist in, that's pretty much a stretch. I mean, their imagination can handle this amount of information. So the number of such civilizations is assumed to be equal to the mathematical product of the average rate of star formation in our galaxy, the fraction of formed stars that have planets, the average number of planets per star that has planets that can potentially support life, the fraction of those planets that actually develop life, the fraction of planets bearing life on which intelligent civilized life has developed, the fraction of these civilizations that have developed communications, such as technologies that release detectable signs into space, and finally, the length of time over which such civilizations release detectable signals for the combined expression of the Drake equation. So that's a lot of fractions multiplied by fractions, so it should be a very small number, supposedly. So this equation was created in 1961 by Frank Drake, not for purposes of quantifying the number of civilizations, but as a way to stimulate scientific dialogue at a meeting on the search for extraterrestrial intelligence. So this is SETI, the project I was telling you about earlier. So he was just trying to get people to think and to talk about how likely or unlikely it might be that they finally get a response. Because SETI has been searching for probably close to half a century and have not heard anything of remark back. Sadly, the equation summarizes the main concepts from which scientists must contemplate when considering the question of other radio-communicative life. Criticisms toward the Drake equation follow from the fact that several of its terms are conjectural, the net result being that the error associated with any derived value is very large, such that the equation cannot be used to draw firm conclusions. Well, no, obviously. These people who are criticizing the Drake equation are missing the point. Obviously, it cannot give us a firm conclusion. We don't even... There is no way to determine what any of these variables actually are. How are we supposed to go out and detect the fraction of planets that actually develop life, or the fraction of planets bearing life on which intelligent life has developed, when we don't even know if any of those exist? But that's the point. it's supposed to make the number seem very small. And scientists, as always, are taking this far too seriously instead of seeing it as the mental exercise that it really is. I think Drake was just trying to point out that the likelihood is so infinitesimal that all of humanity may not even survive to see another alien civilization. So the Drake equation does have some usefulness to the scientific community. It amounts to a summary of the factors affecting the likelihood that we might detect radio communication from intelligent extraterrestrial life. The last 4 parameters are not known and are very hard to estimate. So the last 4 are the fraction of planets that could support life that actually develop life at some point, the fraction of planets with life that actually go on to develop intelligent life or civilizations, the fraction of civilizations that develop a technology that release detectable signs of their existence into space, and the length of time for which such civilizations release detectable signals into space. So those are hard to estimate, with values ranging over many orders of magnitude. Therefore, the usefulness of the Drake equation is not in the solving, but rather in the contemplation of all the various concepts which scientists must incorporate when considering the question of life elsewhere. And it gives the question of life a basis for scientific analysis. The Drake equation is a statement that stimulates intellectual curiosity about the universe around us, for helping us to understand that life as we know it is the end product of a natural cosmic evolution, and for helping us to realize how much we are a part of that universe. What the equation and the search for life has done is focus science on some of the other questions about life in the universe, specifically abiogenesis, the development of multicellular life, and the development of intelligence itself. Within the limits of our inferior existing technology, any practical search for distant intelligent life must necessarily be a search for some manifestation of a distant technology. After about 50 years, the Drake equation is still of seminal importance, because it's a roadmap of what we need to learn in order to solve this fundamental existential question. It also formed the backbone of astrobiology as a science. What we need to learn, although speculation is entertained to give context, astrobiology concerns itself primarily with hypotheses that fit firmly into existing scientific theories. Some 50 years of SETI have failed to find anything, even through radio telescopes, receiver techniques, and computational abilities have improved enormously since the early 1960s. But it has been discovered, at least, that our galaxy is not teeming with very powerful alien transmitters continuously broadcasting near the 21 centimeter hydrogen frequency. No one could say that in 1961. I appreciate that they recognize the Drake equation. It's a roadmap of what we need to learn in order to solve the question itself. So we just need to learn to figure out how to define the variables, and then we can solve it. Although, if we run into alien life before we solve those variables, that kind of defeats the purpose. But I think this does point out a good point about SETI, which is that our radio telescopes and receiver techniques are very narrow and focused. I mean, obviously, we can't explore all bandwidths. We can't explore all radio frequencies. We can't explore every square inch of the galaxy. We can only do our exploring within very small parameters. Perhaps that's why we're not finding much. Perhaps we need to explore different areas of the spectrum. Or perhaps we need to look in different directions and focus these radio telescopes on planets that could potentially hold life. Although we don't even know if that's going to change anything. Perhaps intelligent alien life is moving to other planets that don't really seem to be life supporting, because they've developed their own life support systems. Well, perhaps. But still, I don't think that that is going to stop us from searching. And perhaps someday we will pick up a fragment of one of these radio communications. But until then, we're just going to keep looking around in the dark and hoping that we find something. It's really kind of sad that we can't even leave our planet and go search for these things that we're trying to find. Someday we will, though. Someday we will live in a Star Trek universe. Do you guys want to hear another reason why we might never find alien life? Or intelligent alien life, anyway? Now, I don't mean to be a party pooper, but we have to be realistic. There are some things that make it pretty close to impossible for intelligent life to just arise. And perhaps that's a good thing. Perhaps we don't want to be fighting off aliens left and right, you know? They're just showing up from across the universe, and there's 10 more after them, and they're all different species, and we don't know how to kill any of them, and we can't speak the same language. I think it'd be pretty cool. I think it would be fun to intermingle with a bunch of different alien species. We'd have to learn how to communicate with each other, but once we get past that barrier, I think we'd get along pretty well. So there's another idea out there called the Great Filter, which may help us explain why we don't see very much intelligent extraterrestrial life around us. So the Great Filter, in the context of the Fermi paradox, is whatever prevents dead matter from giving rise in time to expanding, lasting life. The concept originates in Robin Hansen's argument that the failure to find any extraterrestrial civilizations in the observable universe implies the possibility something is wrong with one or more of the arguments from various scientific disciplines, that the appearance of advanced intelligent life is probable. This observation is conceptualized in terms of a great filter which acts to reduce the great number of sites where intelligent life might arise to the tiny number of intelligent species with advanced civilizations actually observed, which currently is just one, us humans. This probability threshold, which could lie behind us in our past or in front of us in our future, might work as a barrier to the evolution of intelligent life, or as a high probability of self-destruction. The main counterintuitive conclusion of this observation is that the easier it was for life to evolve to our stage, the bleaker our future chances probably are. The idea was first proposed in an online essay titled The Great Filter. Are we almost past it? The first version was written in August 1996, and the article was last updated in 1998. Since that time, Hansen's formulation has received recognition in several published sources discussing the Fermi paradox and its implications. So, what does that mean? The easier it is for life to evolve to our stage, the bleaker our future chances probably are. Well, that means that if it's easy for life to evolve to the stage of intelligence that we are at now, we should be seeing them everywhere, on most planets. But the fact that we don't see any intelligent life around us kind of indicates that they went through something catastrophic. Something kind of like their own self-destruction. Kind of like that time that we had all of those nuclear warheads and then pointed them at each other and threatened to use them if we didn't get our way. And then somebody went a little crazy and fired off the first shot, and then everyone started firing and we destroyed ourselves. Alright, you caught me. That's not a real scenario, but you could definitely see it happening, right? I mean, it sounds like something that we would do. Or perhaps they destroyed their own ecosystem. They took away all of their natural resources. Or perhaps they just poisoned themselves with radiation. Who knows? But that's what it means. We don't see intelligent life around us either because it's not evolving or because it is evolving and destroying itself. Which camp are we in? Who knows? Perhaps we won't destroy ourselves. Perhaps we'll go on. There is no reliable evidence that aliens have visited Earth, and we have observed no intelligent extraterrestrial life with current technology, nor has SETI found any transmissions from other civilizations. The universe, apart from Earth, seems dead, Hansen states. Our planet and our solar system, however, they don't look substantially colonized by advanced competitive life from the stars, and neither does anything else we see. To the contrary, we've had such great success at explaining the behavior of our planet and solar system, the nearby stars, our galaxy, and even other galaxies, via simple, dead, physical processes, rather than the complex, purposeful process of advanced life. Life is expected to expand to fill all available niches. With technology such as self-replicating spacecraft, these niches would include neighboring star systems and even on longer timescales, which are still small compared to the age of the universe, other galaxies. Hansen notes, if such advanced life had substantially colonized our planet, we would know it by now. And I'm sure we would, and it wouldn't just be reptilian alien videos on YouTube where they're playing some person talking slowly forward and backward and then pointing out the weird tongue spot. Well, no, that's not evidence. We would be overrun by them if they were here to dominate us, and clearly they're not. Anyway, back to the Great Filter. With no evidence of intelligent life other than ourselves, it appears that the process of starting with a star and ending with advanced explosive lasting life must be unlikely. This implies that at least one step in this process must be improbable. Hansen's list, while incomplete, describes the following 9 steps in an evolutionary path that results in the colonization of the observable universe. The right star system, including organics and potentially habitable planets. Reproductive molecules, such as RNA. Simple prokaryotic single-cell life. Complex eukaryotic single-cell life. Sexual reproduction. Multi-cell life. Tool-using animals with big brains. Where we are now. Colonization explosion! According to the Great Filter hypothesis, at least one of these steps, if the list can be assumed to be complete, must be improbable. If it's not an early step, such as one that's in our past, then the implication is that the improbable step lies in our future. And our prospects of reaching step 9, which is interstellar colonization, are still bleak. If the steps are likely, then many civilizations would have developed to the current level of the human species. However, none appear to have made it to step 9, or the Milky Way would be full of colonies. There'd be colonies on Jupiter, there'd be colonies on Mars, there'd be colonies on our nearest neighbors. So perhaps step 9 is the unlikely one, and the only thing that appears likely to keep us from step 9 is some sort of catastrophe, or the resource exhaustion leading to impossibility to make the step due to consumption of the available resources. So by this argument, finding multicellular life on Mars, provided it evolved independently, would be bad news, since it would imply steps 2 through 6 are easy, and hence only 1, 7, 8, or 9, or some unknown step could be the big problem. Although steps 1 through 8 have occurred on Earth, any one of these may be unlikely. If the first 7 steps are necessary preconditions to calculating the likelihood using the local environment, then an anthropically biased observer can infer nothing about the general probabilities from its predetermined surroundings. Well, obviously there's no way for us to know if we've made it through this great filter or if we're still on our way to hitting the first roadblock in the great filter. So, our future is as far as we know, very uncertain. We could either destroy ourselves, or we could continue to live on and spread throughout the universe. Who knows, perhaps we're the only intelligent life. Perhaps we're not, and they're just ignoring us. Well, one thing's for sure, we, compared to those spacefaring aliens that we like to imagine, are incredibly primitive. Compared to interstellar traveling, hyper-intelligent beings. Yes, we are primitive. We are not very advanced. And one way that we can kind of judge that is based on the Kardashev scale. So the Kardashev scale is a method of measuring a civilization's level of technological advancement based on the amount of energy a civilization is able to use for communication. The scale has 3 designated categories. A Type 1 civilization, also called a planetary civilization, can use and store energy which reaches its planet from the neighboring star. That's kind of like us, where we absorb energy from the sun and then we reuse it, and we only exist here on this planet. Type 2 can harness the energy of the entire star. The most popular hypothetical concept being the Dyson sphere, which is basically like solar panels all the way around the sun. A device which would encompass the entire star and transfer its energy to the planet. And it's kind of like a vacuum cleaner for those photons. You suck them up and you funnel them back to the planet. And then a Type 3 civilization can control energy on the scale of their entire host galaxy. The scale is hypothetical and regards energy consumption on a cosmic scale. It was proposed in 1964 by the Soviet astronomer Nikolai Kardashev. Various extensions of this scale have since been proposed, including a wider range of power levels, and the use of metrics other than pure power. So let's get a little bit more into the definitions of what the levels on the scale mean. So the scale is based on the order of magnitude of power available to them. So how much power, how much electricity do we have? Type 1, which is us, is defined as technological level close to the level presently attained on Earth, with energy consumption at about 4 times 10 to the 19th ergs per second. Guillermo A. Lemarchand stated this as a level near contemporary terrestrial civilization, with an energy capability equivalent to the solar insolation on Earth, between 10 to the 16 and 10 to the 17 watts. Type 2, which we can only dream of reaching, is a civilization capable of harnessing the energy radiated by its own star. For example, the stage of successful construction of a Dyson sphere with energy consumption at 4 times 10 to the 33rd ergs per second. Lemarchand stated this as a civilization capable of utilizing and channeling the entire radiation output of its star. The energy utilization would then be comparable to the luminosity of our sun, about 4 times 10 to the 26 watts. Type 3, which is a dream within a dream, basically, it's so far ahead of our time. We can't even conceptualize what this technology would be or mean. A civilization in possession of energy on the scale of its own galaxy, with energy consumption at about 4 times 10 to the 44th ergs per second. Lamarchand stated this as a civilization with access to the power comparable to the luminosity of the entire Milky Way galaxy, about 4 times 10 to the 37th watts. Just for some clarification, humanity, as it is now, was at about 533 times 10 to the 18th joules, which is about 0.724 on the Kardashev scale. So we're not even at level 1. Well, let me explain that a little bit more. Michio Kaku suggested that humans may attain Type 1 status in 100 to 200 years. we're not even really at type 1 status yet. We're almost there. We don't utilize all of the energy that's coming into our planet, and once we do that, then we will reach type 1 status. Type 2 status comes in a few thousand years, and type 3 status in 100,000 to a million years. Carl Sagan suggested we define intermediate values, not considered in Kardashev's original scale, by interpolating and extrapolating the values given above for types 1, 2, and 3, which would produce the formula. I don't know if you're interested in hearing the formula unless you're a math geek, in which get out your pencils and write this down. K equals log base 10 p minus 6 all over 10, where value K is a civilization's Kardashev rating, and P is the power it uses in watts. Using this extrapolation, a type 0 civilization not defined by Kardashev would control about 1 megawatt of power, and humanity's civilization type as of 1973 was about 0.7, apparently using 10 terawatts as the value for the 1970s humanity. So now that we are properly in our humble place, knowing that we're not even at a level 1 civilization yet, how likely is it that we are going to discover aliens or that they're going to come to us? Well, clearly, the chances are far lower than we ever suspected. Although I do want to go back to one concept that we mentioned, the type 2 civilization that was capable of absorbing the energy around an entire star. Dyson sphere, that is. I want to talk about one potential case of a Dyson sphere. Now, I don't want to send you all running off into a frenzy, but we may have found one. Perhaps. We don't really know. All we see are strange things that we can't explain, and we try to explain them. So, this star has such a beautiful name. It's KIC 8462852. I like to refer to this star as Kik, because it's KIC, so we'll just call it Kik. It's an F-type main sequence star located in the constellation Cygnus, approximately 454 parsecs, or 1,480 light-years from Earth. Unusual light fluctuation of the star were discovered by citizen scientists as part of the Planet Hunters project. And in September 2015, astronomers and citizen scientists associated with the project posted a preprint of a paper on Arxiv describing the data and possible interpretations. The discovery was made from data collected by the Kepler Space Telescope, which observes changes in the brightness of distant stars in order to detect exoplanets. Kik is the only known star with such behavior among the 150,000 stars monitored by the Kepler mission. Several hypotheses have been proposed to explain the star's large irregular changes in brightness as measured by its unusual light curve. The leading hypothesis, based on a lack of observed infrared light, is that of a swarm of cold, dusty comet fragments in a highly concentrated eccentric orbit. Many small masses in tight formation orbiting the star have also been proposed. The changes in brightness could be signs of activity associated with intelligent extraterrestrial life, building a Dyson swarm. That's the one that I believe the most. I don't know about you guys, but asteroids forming around a star aren't as exciting as this Dyson swarm. The SETI Institute's initial radio reconnaissance of Kik, however, found no evidence of technology-related radio signals from the star. Observations of the luminosity of the star by the Kepler Space Telescope show small, frequent, non-periodic dips in brightness, along with two large recorded dips in brightness appearing to occur roughly 750 days apart. The amplitude of the changes in the star's brightness and the aperiodicity of the changes mean that this star is of particular interest for astronomers. The star's changes in brightness are consistent with many small masses orbiting the star in tight formation. The first major dip on 5th of March 2011 obscured by the star's brightness by up to 15%, and the other on the 20th of February 2013 by up to 22%. In comparison, a planet the size of Jupiter would only obscure a star of this size by 1%, indicating that whatever is blocking light during the star's major dips is not a planet, but rather something covering up to half the width of the star. Due to a failure of two of Kepler's reaction wheels, the star's predicted 750-day dip around April 2015 was not recorded. Oh well, they say, because further observations are planned for May 2017. I'm sure in 2 years' time, the Dyson swarm has grown by masses we can hardly comprehend. Perhaps soon we won't even be able to see the star because it will be completely enveloped by the Dyson swarm. But missing that opportunity for data, what if? Let's let our imaginations wander. What if it is a Dyson sphere in the making? That would be an incredible discovery. But knowing how unlikely it is, it could just be a swarm of asteroids. But that's not really all that exciting, right? I mean, if we imagine that it's aliens, then we're much more likely to have public interest in it. So, let's just imagine that everything is aliens and go searching for them. So that way we can be excited and interested, even though we know it's probably not real. Well, instead of looking far, far away for life, perhaps we need to look someplace closer, someplace that we actually have an opportunity to go visit. I'm going to read you an article about NASA finding more evidence of alien life. And where do you think it is in our solar system? Go ahead, give it a guess. If you guessed Europa, you're right. Scientists just found even more evidence that Europa, one of Jupiter's 67 known moons, might host alien life deep within its icy oceans. The little moon has long been labeled by NASA as the most likely planet to find life in our solar system, thanks to the deep, salty oceans that are strongly suggested to be hidden beneath its frozen crust. And now, a new study has shown that the chemical balance of those oceans would be very similar to the ones here on Earth, suggesting there would be enough hydrogen and oxygen for there to be life, for life to form, even without volcanic activity. We're studying an alien ocean using methods developed to understand the movement of energy and nutrients in Earth's own systems, which might make the system a little biased, but The cycling of oxygen and hydrogen in Europa's oceans will be a major driver for Europa's ocean chemistry and any life there, just as it is on Earth. To understand how this might work, the team compared Europa's potential for producing hydrogen and oxygen to that of Earth. For the purposes of this study, they only looked at processes that didn't involve volcanism. Volcanic activity is thought of as a kickstart for the formation of life. But the team wanted to see if passive processes on the moon could do the same thing. And to their surprise, they calculated that they could. Published in Geophysical Research Letters, the study showed that the amounts of both hydrogen and oxygen would be comparable in scale, and on both worlds, oxygen production is about 10 times higher than hydrogen production. On Earth, our oceans make hydrogen through something called serpentinization. That is where salty seawater soaks into cracks in Earth's crust and reacts with the minerals there to produce hydrogen and heat, two important ingredients for life. The potential for this to happen on Europa was the first thing the researchers focused on. And based on how the moon has cooled down since its formation, they calculated that it might have fractures in its rocky interior as deep as 25 kilometers, or 15 miles, roughly 5 times deeper than cracks here on Earth. In other words, plenty of room for hydrogen to be formed as the ocean water percolates in those cracks. The team then looked at the potential for oxygen to form. This could happen when the frozen water molecules on the icy surface of the oceans are split apart by cosmic radiation. And the team predicts that these elements would then be cycled back into the depths of the ocean. So we've got the hydrogen and we've got the oxygen. The missing link now is life. Whether or not life and biological processes complete the circuit is part of what motivates our exploration of Europa, said one of the researchers, Kevin Hand. NASA is planning a flyby mission to Europa in the 2020s, and until we actually send a probe there to scan what's going on under the ice, we can't say for sure whether or not the moon could be suitable for life, or even whether the suspected oceans exist. There's also a lot more involved in the formation of life than just those two elements. The team now wants to model the cycling of other important elements on Europa, such as carbon, nitrogen, phosphorus, and sulfur. Either way, this latest research just adds weight to the argument that we need to get out there sooner rather than later to test the waters, literally and figuratively, for ourselves. We can't wait. And neither can I, to be honest. I would like to see what is going on Europa. What gave them the idea that Europa is made of water? That it's ice covering a sea? Was it through sonar? Was it through distant radio telescopes? What if it turns out we're wrong? Then we have to reevaluate the entire way that we scan for information throughout the universe. But if we're right and we do find new living creatures in there, well, that would be astonishing. We'd have a whole new section of biology, a whole separate tree of life. Well, what does it mean for us in the context of the Great Filter if we do find life on Europa? Good news? Bad news? Are we all going to die soon? Or was it just the right environment for life to evolve? Well, one thing's for certain. We are going to continue searching for alien life, near or far, wherever it is. Whether we have to drill down beneath 15 miles of ice to reach salty sea on an alien planet, or we have to scan for information from thousands of light years away. We are going to continue this search. And perhaps the search for alien life will always lead us back to Earth. Remember how early in the program we talked about that strain of bacteria in the atmosphere that seemed as if it was alien? That was high above the Earth's surface. And now, scientists have found microbes that live below the Earth's surface, that have forced scientists to reimagine how life works on this planet and others. Could it potentially be alien life? Perhaps it is. Perhaps sometimes people just cannot believe their eyes and come up with crazy explanations for things. Anyway, Kenneth Nielsen is one of those people. He's one of these scientists, and he apparently looks awfully sane for a man who has basically just said that he has a colony of aliens incubating in his laboratory. He has an office at the University of Southern California on the 5th floor of Sheffer Hall. An encouraging collection of academic awards hang on his wall. And across the hall is the explanation for his quiet confidence. Beakers and bottles full of bacteria that are busily breaking the long-accepted rules of biology. Life, Nielsen is explaining, all comes down to energy. From the mightiest blue whale to the most humble microbe, every organism depends on moving and manipulating electrons. It's the fuel that living matter uses to survive, grow, and reproduce. The bacteria at USC depends on energy too, but they obtain it in a fundamentally different fashion. They don't breathe in the sense that you and I do. In most extreme cases, they don't consume any conventional food either. Instead, they power themselves in the most elemental way, by eating and breathing electricity. Neeson gestures at his lab. That's what they're doing right there, right now. All the textbooks say it shouldn't be possible, but by golly, those things just keep growing on the electrode, and there's no other source of energy there. Growing on the electrode. It sounds incredible. It's kind of like science fiction, he says. To a biologist, finding life that chugs along without a molecular energy source, such as carbohydrates, is about as unlikely as seeing passengers flying through the air without an airplane. This discovery comes with some sizable implications. On a practical level, electric bacteria could be harnessed to create biological fuel cells or to clean up human waste. Nielsen tells me that one of his former students just got a grant to build a bacteria-powered sewage system. But, more to the point, such microbes appear to comprise a vast, largely unexplored realm of life on this planet. There's a chance that they are an important part of the biodiversity on planets beyond ours, too. Nielsen never utters the word aliens, but it hangs heavily over the conversation. His bacteria are unlike anything we've ever encountered. They are forcing us to rethink life as we know it. So how did the discovery happen? Well, like any good alien story, this one begins with an abduction. Though one of a decidedly different scientific variety. The abductee in this case was not a person, but a mineral. In 1982, he was a professor at the Scripps Institute of Oceanography when he heard about strange goings-on in the Oneida Lakes in upstate New York. Each spring, snowmelt washes manganese out of the surrounding mountains and into the lake. When the wind whips up the water, allowing the dissolved metals to combine efficiently with oxygen to form solid manganese oxide, which then sinks to the lake bed. The trouble was, scientists didn't find nearly as much as they anticipated. Something was making the manganese oxide vanish at more than 1,000 times the geologically expected rate, and nobody could figure out what. If rates were really fast, I knew it had to be due to biology, Nielsen says. He suspected bacteria in the lake were getting rid of the manganese oxide almost as quickly as it formed. That theory made perfect sense, but it ran counter to the textbook wisdom. That microbes can't break down a raw piece of metal any more than you or I can. The mystery kept itching at him. In 1985, Nielsen relocated to the University of Wisconsin-Milwaukee and began research at Oneida Lake to prove his hunch correctly. After a 2-year search, Nielsen succeeded in identifying the manganese thief. Shewanella, a bacteria that functioned unlike anything he had ever known. As soon as I saw what Shewanella could do, I just went wacky, Nielsen says. I called all my students into the lab and said, this is a very, very important organism to understand. Nobody is going to believe it. It's going to take us 10 or 15 years to convince the world it's true. Well, I guess we all know it's true and believe it now, because here it is. There's the evidence. For most living air-breathing creatures, the glucose that we eat supplies the electrons. The oxygen we breathe receives the electrons, and that electron flow is what runs our bodies. That's basic metabolism. The challenge for every organism is finding both sources of electrons and places to discard them in order to complete the circuit. Shewanella consumes electrons from carbohydrates, but it sheds them in an unusual way. It swims up to the metal oxide and respires it, Nielsen says. We call this breathing rocks. Here's where the scientific heresies begin. Shewanella's outer membrane is full of tiny chemical wires, enabled by specialized proteins that let it move electricity out of the cell. The wires make direct contact with the manganese oxide, which is how it can deposit electrons and breathe a solid substance. Furthermore, Nielsen recognizes that the bacterium doesn't even care whether the substance on the outside of its membrane is manganese oxide or something else entirely, so long as it will complete the electric circuit. So this is all very exciting and fantabulous, isn't it? This bacterium just breathes rocks. It's unlike anything we've ever seen. It's so incredibly amazing, and it's unique, and it must be alien. At some point, we are going to have to turn away from that explanation. We can't look at everything that is strange and odd and surprising and say that it's alien, because that actually corrupts the word alien. We need to save that word for things that are truly out of this world, from a different origin entirely. The more we use the word alien, the less it means, the less people will believe it. So stop using it to describe things that are just strange. True aliens that travel the cosmos, someday when they meet us, when we understand their biology, when we tell them and show them all of the YouTube videos about alien sightings here on Earth, or the things that we found that we believe are aliens, they're going to laugh, don't you think? We are quite imaginative. We let our imaginations run away with us many times, especially when it comes to things that are hard to believe. Sometimes perhaps it's best to just enjoy the silence until we do know what the truth is. Or sometimes we need a little more imagination. According to the original estimates of the Drake equation that were made in 1961, there could be anywhere between 1,000 and 100 million civilizations in the Milky Way galaxy alone. But just because we have that number as an estimate, especially since it's such a wide range, that doesn't necessarily mean that there are aliens out there and they're waiting for us to come find them. I think they're probably just trying to live like we all are. Besides, we have no way of knowing if that number is even true. I mean, we've never encountered any other alien species that are intelligent. But that does not mean that alien life does not exist, because we have found alien bacteria, and that still counts as alien life. Well, that's all the time that I have today. Thank you so much for listening. This has been the Illumination Hour with me, your host, Ellen. You can email me at illuminationhour@gmail.com. Thanks for listening, everyone. See you again next week.